Yes, one thing about Peter was that no matter what time of day, no matter what time of year, uh, he was, well, some people say always working, uh, but he was just mentally active on questions in mathematical finance a lot. I met him in 95 when I took a sabbatical at Cornell. And then I was with him at Morgan Stanley. And I remember the family used to go up to, I used to go up to Connecticut for Thanksgiving. And the family would go shopping on the Friday after Thanksgiving. And however, Peter and I would be in the office at Morgan Stanley while the families are shopping. And we, in fact, worked on the FFT paper for option pricing on a Thanksgiving weekend, putting that together at Morgan. We were actually building it for the calibration of the variance gamma model, which Morgan Stanley used to mark their books for over 10 years. So yeah, I've been engaged with Peter a lot, and like I mentioned, I was talking to him just a week before he passed away on some of these matters. So today I will speak on financial finance and what is it. And basically, I've been looking at alternative objective functions for financial decision making. And you could take it further into decision making in general. And I was not satisfied with objective functions of mean variance or expected utility. And I will explain a little bit of my dissatisfaction there. And then I got somewhat excited about nonlinear expectation theory and said, oh, maybe this is an avenue from which we can proceed. And I made many applications of nonlinear expectation theory and wrote a book with Wim Schoutens on conic finance, which basically develops the theory of nonlinear expectations as an objective function for financial decision making. But the dissatisfaction with nonlinear expectation theory, if you look at it at least in the static context, in the dynamic context, there are some answers. But in the static context, is that it is an objective function that scales. So the value of 10 times is 10 times the value. So whenever you have, and that's a property of linearity that the nonlinear keeps, the nonlinear expectations are nonlinear in many directions, but not in the direction of money. And so it doesn't answer the question, how many dollars should I put in the stock today? I have a stock or a bunch of stocks or some options or a bunch of options. What should be my investment level? And when you use it in trading and things, well, people will say, oh, it says good, maybe buy 10. It says bad, maybe sell 10. Okay, why 10? Well, you got 10 fingers. And so I said, well, I would like an answer to the question of how much. After all, if something is attractive, you decide to go in. But how far do you go? Isn't it at some point the risk too much that you should stop and this is enough? And so I wanted to answer in some mathematically precise way the investment problem of how much, not just what. Okay. And for that, conic finance and nonlinear expectation theory was not enough. And so that's, I developed new objective functions, which are not that new. They've been known as risk measures, convex risk measures. But risk measures is the philosophy of risk measures doesn't give you the right incentives of how to judge value investing. You're too focused on risk, whereas our real job is to produce value. And of course, mathematically, you can say negative risk is positive value, negative value is risk. And so you play games like that, that's fine. So I said, no, I don't want to look at it from that perspective. The value risk was turned around by Dilip Madan, and he developed the theory of monetary utility. And I said, okay, this looks good, and I will explain it in English and then connect it to the mathematics later. The mathematics is the mathematics of convex sets, which we have a lot good understanding of. And so anyway, I said, I'll take this up. But the main thing about monetary utility and what I like about it is that it is financial. It's financial in the sense that the marginal valuation of money remains one always. There is no diminishing marginal utility. There is no diminishing marginal valuation of money. There is complexity. There is risk aversion. We are averse to risk. But what we are not averse to is money. We're not averse to money. Okay. And the whole theory of diminishing marginal utility is asking me to model my dissatisfaction with getting rich as embedded in the rate at which the utility for money falls as I get richer. And I have not found anyone managing wealth at a level, substantial level, suffering from this ailment. And so I say I want to get rid of diminishing marginal utility, but I still want to solve the investment problem. And I show you that financial finance valuation is an answer. And it is technically the same as monetary utility, and which is technically the same as the negative of a convex risk measure. Okay, so fine. But apart from mathematics, I would like to phrase what kind of objective function you should use will come from your understanding of the economics of the thing and what you mean by value production. So I'll contrast it, of course, briefly with the portfolio theory context. I mentioned nonlinear expectations and the issues with them, that it scales. Dynamically, you can do something. Then I'll present the financial finance solution in broad English terms, and then relate it to the mathematics, which is the convex risk measures and monetary utility, its negation. Now, what excited me further about these things is that for me, I want to use these theories to do things, to actually, I can't go to a firm and to a wealth management institution and present a good theorem. This is not what the business is. And so you want to use it. And convex risk measures have been around for a long time. But when you get to using them, you pretty soon see that when you want to do the value maximization problem and you're maximizing a conservative valuation, the conservative valuation is an infimum of expectation, and you're maximizing an infimum of expectation. Where are you? You're at a saddle point problem. You've got an objective function with two arguments, concave in one, convex in the other. And you want to simultaneously solve the two optimizations. you want to maximize a minimum. You can do it the slow way. Write a maximization algorithm that calls the minimization algorithm. It solves the minimization, comes back, takes ages. And I was very happy to see that the people, Stephen Boyd and Van der Werf from Princeton and Stanford, that have developed all the algorithms on fast convex optimization and developed the CBX routines, which I've been using for years, moved on in 2024 and developed DSP, Discipline Saddle Point Programming. And these are fast algorithms for fairly high dimensional saddle point problems where you're simultaneously solving the maximization and min. And that was what I used to actually implement financial finance valuation. To implement it, you need saddle point programming, which is now available. It is available only in Python, and I work mainly in MATLAB. But with the help of one of my PhD students, I managed to get Python into MATLAB, and I solve it inside MATLAB, but external call to Python. Okay, but those are things that go on. Now there are applications, and in the paper, there's an application just to the question of a single asset. You just ask the question, how many dollars should I put in the stock? Of course, you ask the same question about 1,000 stocks at the same time, and you can implement the answer that it gives you and develop a stock trading strategy. And so you have automated stock trading because the machine is telling you how much to invest, and you can build a strategy out of that. And so I've done that. Then I've looked at the multi-asset applications as well, which generalizes the portfolio theory because you not only answer the question, how much money to put where, but you also answer the question, how much money to put period. Okay, you want to put 10,000, 20,000, 9,000, what? Okay. And so I'll comment on that aspect, but here I've gone on and applied the same financial finance valuation techniques to option trading and developing positions in options. And here there's another dimension of financial. We have become accustomed, being trained initially by economists and statisticians, finance being a later discipline. Another thing with Peter and I is that we were both accidental math finance people. Our first degrees, both for Peter and I, were accounting. We came from accounting and came into mathematics and finance later. But one of those perspectives is that you put on a position, you take a risk, and your perspective is that you're going to eat the cash flow. And you're going to eat the cash flow. That's why marginal utility comes into the picture, because you say, I'm going to experience this reality and I'm going to work under the physical measure which I have, and I'm going to experience and work with this reality. However, in finance, one thing one recognizes is that you don't just go into a trade and eat the cash flow. You actually go into a trade to a marketplace, and then a little while later, you exit the trade in the marketplace. At entry, you face the market. At exit, you face the market. When you work under the physical measure, at entry, you face the market, but at exit, you face your physical reality. You just eat the cash flow. Okay? Now, if you cast the problem in the financial way, then at both entry and exit, what's relevant is a financial measure. What matters is the terms at which the market lets you come in and the terms at which you will exit also in the market. And so my option trading strategy never contrasts a physical measure, which we actually don't know, with a risk neutral measure, which the market knows. The option trading strategy plays one risk neutral measure against another risk neutral measure. So you're always playing market with market, and you don't concern yourself with the physics of things. Okay. And so that will show up in the option trading application. Okay, so let me point out that, okay, these strategies should determine the aggregate investment level. Now, the minute you contemplate this question as to how much should you invest in a certain risky situation, upfront, you know that there are certain questions for which there's no answer. So if I have a zero-cost investment that produces to me non-negative cash flow, what's the optimal amount to put in there? There isn't an answer to that, okay? You just go all the way, keep putting. More generally, an arbitrage is just a non-negative cash flow at zero cost. More generally, we talk in terms of acceptable risks, where we take some risk. We don't say that I need a complete non-negativity. I can take some risk. So we generalize the concept of arbitrage to a convex cone containing the non-negative random variables, not just the non-negative random variables. So if you have an opportunity that is like a generalized arbitrage, namely it belongs to a convex cone containing the non-negative random variables, there's no answer to the question how much to invest. So such cones are defined by a sequence of test measures. And so you have a family of test probabilities. And you ask the question, are you positive under every test probability? And if that's the case, you have a generalized arbitrage. And if you have a generalized arbitrage, you don't ask the question how much to invest. Okay. So the only things for which you have to answer the question how much to invest is where the infimum over your test measures, is negative. Okay. So then you can ask the question, okay, how much to invest? There is risk. Now I need to see at what to cut off. So we believe that for most applications that we put on, yes, we work with a context where we have the infimum being negative, and that's the opportunities we see in the market. The market is not giving us an arbitrage or a generalized arbitrage. I'll skip over the portfolio theory question, but we want to answer the investment problem. And this problem is often stated as that of investing the total wealth in portfolio theory. And especially when you're looking at expected utility, you say, okay, here's my wealth. How should I best invest it in all the available risky assets? Okay. That's a okay question, but an expected utility certainly takes that perspective. But what's wrong about that question from our world today, at least from what I think and say, is that nobody is ever going to ask you how to invest all their wealth. Nobody is ever going to put their whole wealth liquidated even for themselves, let alone you. Okay? So when we are investing in the millions, the wealth backing it is in the billions. When we're investing in the billions, the wealth backing it is in the trillions. Okay? The wealth is a whole order of magnitude beyond the level at which you're being asked the question. And so the wealth in place is a whole order of magnitude above what can be made available to any quantitative strategy. We're never asking a question about all the wealth. And we're also never asking the question about all the risky assets. Okay? All the wealth, I'm not liquidating and giving it to you to figure out where to put it. And all the risky assets, there's so many, they're coming every day, you're not going to have access to all of them. Okay? So you're always in a partial situation. Don't take the universe too seriously. And in fact, don't claim knowledge of the universe at any point. So the investors are not committed to putting $10,000, which is all their wealth. No. If there's a good opportunity, they'll put 15. If it's a bad one, they cut back to 5. Okay, so they're comfortable with changing the amount. You're not committed to that. So now to answer the question, how much? Oh, I want to go back. So mean variance theory gives us an answer to how much. It says the mean is positive, it's attractive, go in. Don't go in too far because the variance will pick up, so stop. So the mean variance objective answers that question, but not for me in a comfortable way, because you measure reward in dollars and you measure risk in squared dollars. And then you pretend that you can find some coefficient that is a trade-off between the two. And then you use that globally. I agree that local quadratic approximations are okay for nonlinear functions locally, but you use it globally. And that's not fair. So I say no good for that. Expected utility offers it, and I've already told you my objections to expected utility. There is no diminishing marginal valuation of money. And I don't want to be modeled with that. So when investments are a fraction of the wealth at hand, the movements, whether I make $1 million or I lose $1 million, and my background wealth is sitting in the billions, there's no diminishing marginal utility involved here. It's a moot point. It's not there. So I say, okay, we want to get away from any falling marginal utility or marginal. We want to keep the marginal valuation of money constant. The theory of nonlinear expectations, I said, did that. Gave you a new objective function. You maximize an infimum of expectations there. However, it scales. And because it scales, the value of 10x is 10 times the value of x, and you don't get a solution to how much. However, if you put in background risk, as this is a paper with Wim Schouten and King Wang that we did in quantitative finance last year, and we show there that if you put in the presence of background risk, then conic finance and nonlinear expectation theory will give you an answer to how much. And we showed also that if instead of background risk, you go to a dynamic context, where you have the immediate reward from your investment, which is the return to your policy, but you also have to worry about the fact that there is changes in states, and in a dynamic context, and you have to face the valuation of changes in states that occur. Now, the changes in states and the valuation of state changes operates like a background risk. And so you get an interior solution to the how much question. The investment question, you get a solution with nonlinear expectation theory in a dynamic context. So you have to go dynamic. And I've done a number of papers doing applications of that. But I now wish to come to the financial finance solution. So I say, put aside nonlinear expectations. We want to get a solution to the investment problem. We want to throw away diminishing marginal utility. We don't want mean variance. So what are we going to do? So I say one of the potential problems of financial modeling is that we begin with the concept of a probability space. And that's fine. We talk about random variables. We have a probability space. Omega FP, great. Now we go. However, We have to crystallize uncertainty and pick a probability space, that's fine. However, we are aware that the probability space that we've chosen to work under can change, and change suddenly into adverse situations, completely different. War breaks out, this happened, that happened, Trump becomes president, I don't know, all kinds of issues you have to worry about. And so your objective function can't be silent about all the other probabilities. You can't say, hey, this is the probability I'm working under, the other probabilities, they don't exist, they're gone. They don't matter. This one. Okay? Well, that's too autocratic and dangerous to say that the probability space you've chosen is the only one you're going to think about in making decisions. So you can say, of course, let's look at all other possible probabilities and put a probability on that, and then you can keep going. There's no end to that, and that's not realistic. And in fact, it can render all action indefensible in the sense that you just won't even get up and go to work. I mean, you just stay in bed because there's too many probabilities bothering you. So the other probability is not about robustness with respect to estimation errors of parameters. That's not what's worrying me when I'm talking about the other probabilities. I'm not saying, this is my probability, but I'm not sure it could be this, it could be this. No, it could be completely different. Okay. So the other probabilities can be drastically different and actually generate almost sure losses, and you know that. You know that you're working under this probability, you expect to make money, something drastic happens, okay, it's going to be losses. You understand that? But what do we do with these other probabilities? And this brings us to the role of supporting wealth. The role of supporting wealth is that I'm working on this probability. Not all my money is here, a part of my money is here. And if the shit hits the fan and there's going to be losses, I can cover them. I have supporting wealth, okay? And I used to tell the story to one of my colleagues. I said, to make money, you need supporting wealth. And if you have supporting wealth, then you can trade, you can take care of adverse situations, you can make money. So to make money, you need money first. Okay? If you don't have that first lot of money, you can't really be in the business of making money. So what do? Well, you steal it. The first set of money is stolen, and the rest is built. And the history gives us many stories in this direction. Okay. So, with these other probabilities, the supporting wealth announces for each adverse measure, Q, a limit on the loss. They say if it hits the fan, you're going to be losing $3 million. It's okay. I got it. I can cover it. And so the objective function recognizes the existence of supporting wealth for adverse probabilities. And that supporting wealth is announced by the rebate function, rho of Q. So rho of Q is a rebate function that tells you how much loss you can take under adverse probability Q. Now, the acceptability question of what are the acceptable risks? A risk is acceptable if the rebate covers the loss, which means that EQ of X plus the rebate is positive. That's what acceptability translates into. This also means that expectation under Q is greater than or equal to minus rho of Q, which means that there's a negative floor, which is a convex risk measure. So the theory of financial valuation is none other than the theory of convex risk measures. And so risk acceptability now becomes, you have acceptability if that infimum is positive. And you have to worry about, in defining an objective function for financial finance valuation, you have to specify two things. M, the convex set of measures under which you have a cone of arbitrarily acceptable risks. I call the risks that are in the conic finance cone the arbitrarily acceptable risks. They're acceptable at every scale. Okay? And none of them are available to us, so we're not worrying about that. For all the other risks, there will be a rebate, and this becomes acceptability. And from here, you immediately get the valuation function. So how do you value a random risk or outcome? Is this valuation function. Now, immediately you see for such a valuation function that if you add a constant to your outcome, you add that constant to the value. So there is no diminishing marginal utility of money. The valuation of V of x plus A is V of x plus the A. Okay, and so this satisfies the principle of nonlinear expectations and cash invariance, namely you add a constant and it goes into the value. Okay, but you have a convex risk measure connected. I mean, if you take the negative, you get a convex risk measure. And so, of course, the LTCM story about background risk is that LTCM in April gave back $1.9 billion to investors, saying we didn't need this money and we didn't have investment opportunities for it and take it away. And in August, they went under because they needed $2 billion. Okay. So supporting wealth is there for a purpose. And you can't think of the supporting wealth as, it's just useless, we don't need it. And this other property that I've mentioned is that there's no diminishing marginal valuation of money. You add a constant and the marginal valuation is unity always. Now, the normal probability is the one that you're comfortable with, it's okay. And you want to make money under that normal probability. Now, that normal probability P has no rebate. So you make sure that the rebate is zero at P, okay? You make sure that the rebate is zero at P. And this ensures that the value function is conservative in the sense that it's below the expectation, okay? So the value function is a conservative valuation below the expectation because there's no rebate at P. A little bit technical, you can work out, but the rebate function should be a convex function. And it can be represented as a supremum, and you can see that it gets convexity from there. So the rebate function is always a convex function that is zero at the central measure P. So now your problem then of investment in any bunch of risky assets becomes a max-min problem, because the valuation is an infimum and the objective is to maximize over P. And so this is a saddle point problem. You have an objective function that is concave in one variable P and convex in another variable Q. And you want to simultaneously do the max-min. And so this is where the discipline saddle point programming comes in. And so we use these methods to actually solve such problems. Now, the mathematics of financial finance I've already explained, is that it is the theory of monetary utility as developed by Freddie, and also the theory of convex risk measures, which goes back to Fulmer and Sheen 2004, where you were basically saying people were objecting to risk measures being a cone and saying that it's too much, it's too generous, it needs to be a convex set. Okay, so that's fine. And I'm saying the same thing, but I'm saying that risk theory or convex risk theory doesn't give me an intuition of how to define the convex set and where to set the floors. But when I turn it into a financial finance valuation problem, I see more clearly how much loss I'm willing to cover and what my supporting wealth is. And so I can define my rebate function. And if you have a sensible rebate function, you have an operational objective function. Otherwise, you just have an objective function to think about, but nothing to say. Okay. So that connects up with that. Another property when I look at trading strategies is to worry about covariation. If you look at a trading strategy in accounting value, it is a bilinear function of position and price. You have so many shares, it's worth so many dollars. You do Ito's lemma on that bilinear function, and you immediately see that you have a covariation term. Okay, there's a covariation term. And fortunately or unfortunately, we have driven that to zero in finance because we say positions are predictable and finite variation, and therefore they are orthogonal to martingales, and the stock price has a martingale. So dp/dt is zero. Okay, the entire hedge fund world spends enormous amounts of time and effort to ensure that that covariation is positive. They want to be buying things that are going up in value and selling things that are going down in value. They're playing covariation, and we have theoretically dismissed it as irrelevant. So I say, when I put on a trading strategy, I always evaluate covariation risk to see. I call that now the dynamic trading benefit. The first term is self-financing, which is saying that you buy and sell. You buy what you could earn from selling what you sold. You finance your position. The second term is the usual gains from trade. And the third term is the dynamic positioning, the valuation of dynamic trading. So whenever you set up a trading, now you have an answer to the question, how much do you invest? So you invest based on the policy that your machine is giving you. And then you say, is my machine dynamically trading well? Is it buying what's going up and selling what's going down? I want to know that. I just don't want to know how much money it is. I want to know whether dynamically it's making money. And for that, you evaluate covariation risks. So when I apply this to a single asset, I look at the covariation calculations. So the implementation steps are, okay, for a single asset, you specify the return distribution. You define the set of arbitrarily acceptable risks. You choose the measure M that defines the arbitrarily acceptable risks, or the cone of conic finance. You formulate the rebate function, which is the second input into financial finance valuation. Then you solve the whole thing as a saddle point problem. And then you train a machine to learn the solution. Because when you solve a DSP, even though the saddle point solution is fast, it's not that fast, okay? So you train it on a certain set of inputs, and it gives you a policy. Now you say, I want a policy for arbitrary inputs because I don't know what my inputs are going to be in real life. And I want a function that tells me how to act. So I train a machine. I use either Gaussian process regression or I use neural nets to learn the solution of the DSP. And then I can fast implement and develop a proper training strategy because I can implement it on arbitrary points. And then you execute that policy. Do I have to point it here? Okay. And then, so I present these details a little bit for a single asset and close with the option trading. Okay. So for a return distribution on assets, I work with the bilateral gamma distribution, which is a difference of two. You take two. Why is this? Yeah, so you take two standard gamma processes, and then you define bilateral gamma as space changed and times space scaled and time changed standard gamma. Okay, that's the characteristic function of a bilateral gamma. Why is this not moving that fast? Okay. You can parameterize it in terms of the mean and variance, so up and down moves. And that's a good parameterization because they are of a similar order of magnitude. The BP-CP parameterization, the BP is in basis points, the CP is in hundreds. And so you can't do quantization. And when you want the DSP solution to be learned by a machine, you want to quantize it down to a small set. And so you use parameters that are of a comparable order of magnitude. And that's why I switched to, for quantization purposes, I switched to mu P and mu N, sigma P, sigma N. So now, okay, we can pass through these kind of details about the parameters. Now to define the arbitrarily acceptable risks, I'm using a concave distortion. So I take a concave distribution function psi on the unit interval, and you say that if the concave distortion is positive, it's arbitrarily acceptable. And there's a dual characterization of that. The set of probabilities Q that go to the set M are all probability measures that are bounded above by the distortion. And so that's the set M that you're working with in defining the set of alternative measures. Remember, I told you you need to define M, okay? So you have P, which is some bilateral gamma return distribution. You have to define Q, which is defined this way in terms of distortions. And to operationally work with it, it is helpful to work with the dual. And so you look at all densities of Q with respect to the original P, and basically Q is an M if the density satisfies this condition, namely that the expectation under P of Z minus A positive part is bounded above by the conjugate dual of psi. So you now, for many distortions, like I've been working with for years, the min-max bar distortion and other distortions, the conjugate dual is analytically computable, so you know your function phi, and so you can operationally define the alternative measures. And phi of A can be written this way, and so it is easily computed. So that's the psi that I use, the min-max bar distortion. And I pick a level gamma, which is 0.2, which is high enough. Most stocks are near 0.1, 0.15. Few hedge funds make 0.75. And the conjugate dual is given that way. So you're all set up in terms of M and how to define the cone. the next thing that one has to do is to define the rebate function. And the rebate function is convex. And not only is it convex, but it has to be disciplined convex. And disciplined convex means that a machine has to be able to verify that it is convex using simple rules of convex functions. And so like the square root of 1 plus x squared is convex, but it's coming from combining concave with convex. And so the machine says no. So that is not a disciplined convex function. And so there is a whole library of admissible functions that one can use in developing these things. And so basically, if eta is greater than 0 and beta is positive, this thing is a convex function. And so the rebate is a number. And that number is the expectation of R of Z. So I define the rebate in terms of the Radon-Nikodym derivative in terms of density, and is defined by the expectation of a convex function of the density. So the rebate is defined that way. Now I want to ensure that the rebate at the physical measure is 0. And so the choice of theta is just based on that. If you pick theta this way, given the convexity parameters beta and eta, you get that the rebate is 0 at P. So the valuations are then conservative. So now I'll go straight to, straight to the saddle point problem. Basically, if you have a return Rn, and you ask the question, how many dollars to put in that return, that's P. That's the variable you're maximizing over for your investment problem. You then have to say that I need to take expectation under Q. So I put in the change of measure density Z, and I put in the rebate, and I put in the probability measure under P, which is the original the original measure P. Then this is your saddle point objective function. And in any practical application, or most practical applications, these problems are finite dimensional problems because you will either simulate or grid your sample space. And so the measure changes are defined. Measure changes are on a large finite dimensional space. And so this is your saddle point problem. And the Z has to be a probability. It has to be in the set M. So expectation of Z minus A positive part under P has to be less than the conjugate dual, and Z is non-negative. And so this is the saddle point problem that you saw. And so I did this for a whole bunch of stocks on a whole bunch of days. And I implement the trading strategy by putting in the stock, the number of dollars the algorithm told me to put. So I have a trading strategy that goes on every day. But I can't. This is an entry rule. It tells you what to do. It doesn't tell you when to get out. Okay, there's no exit rule. Okay. Now you can't just keep entering and hope things will work out. You will build, if you try to implement it, and you go to a trader and he'll say, look at this, man, I can't hold the position. It's getting too huge. Okay. And so what we do is we take algorithms that give us entry rules, convert them into trading strategies by unwinding all legacy positions at 5% daily. Okay. So we don't unwind tomorrow. If you say, I'm going to buy today and then tomorrow sell it, if you do that, we did those kinds of trading strategies, and you'll never make money. You just keep paying the spread every day and losing money. So you can't exit every day. So what we're doing is exiting at a uniform rate, 5% legacy positions unwound every day. And so I did this for, a large number of stocks. And basically, that was the GPR algorithm. And this was the cumulative cash flow from the trading strategy on 180 stocks. And this was the correlation graph, the correlation between position and price. So the algorithm was giving us positive correlation in position and price. It was telling us to buy what's going up and sell what's going down. It's a machine. And the machine is doing its job. And this just verifies externally that, okay, it is making dynamic contributions. Now I'll just switch. I'll switch to the option application. Yeah. So the option application, like I said at the beginning, it's going to trade one risk neutral measure against it. So what I'm doing is I'm going to buy 3-month options. So I did with Peter a paper on option trading, trading the physical measure against the risk neutral measure. And the typical strategy that comes out of that is you have a very thin physical measure. The optimum solution is marginal utility inverse applied to DQDP. And it just tells you to buy out of the money puts and hope that you earn the premium and the option expires unexercised. Okay. And my trader friends would say, Dilip, come on, I don't need mathematics for that. Okay. I don't need a mathematician to come here and tell me buy out of the money puts and wait for the light. So we said we're not going to trade the physical measure against the risk neutral measure. I'm going to take 3-month options. I'm going to take a position in 3-month options at prices given by market. Then, a month later, I'm going to sell those options. They will then be 2-month options. And I want to see, that's 1 month later. So I have a 1-month risk neutral density that I'm going to look at. I have the 3-month risk neutral density that I'm going to look at. And I'm going to look at the 2-month risk neutral density, which today's 1 month, what is the density between 1 month and 3 months today? Okay, to make some prediction about how I might unwind. And so C of S is the cash flow of the 3-month density. And forgetting these remarks and things, basically, I look at the density at the second time point, which is 3 months. I look at the risk neutral measure today for that. And I say my position should be, okay, self-financed. I take a zero cost position at the 3-month density. So Y of S2 is cash flow, arbitrary cash flow coming from option trading, some function of the stock price at the 3-month point, which has zero value. And that's what I'm going to find. But I've got to work out what I'm going to get by taking that position. And what I'm going to get is I say I need to work out what I could sell it for in 1 month. Okay. So in 1 month, the stock price will be S1. And I need to get a distribution for what the 3-month position would be 1 month from now, maturity of 2 months. And this, of course, is the density in 1 month for the remaining 2 months. I don't have this density today, okay? But in principle, there is something like that. And then I could unwind and receive from the market W of S1. And then my objective function is so here I'm using today's 3-month density to build what it might be. So I say, okay, the surface doesn't change. And I'll look at today's 2 months to work out tomorrow's 2 months. And so we can evaluate this way, using current option prices, the value at which I might exit. And I'm going to use a financial finance valuation objective function. So I'm going to have a change of measure C of S1. And I'm going to make sure that I'm in the conic finance cone. So I'm going to have my conjugate dual. And then I'm going to put on a rebate function on the change of measure density. And I'm going to solve the DSP, which is maximize the function of stock prices at 3 months that I want to access that maximizes the value of that position, which is exiting in 1 month. There's a change of measure density for 1 month, and there's a base density for 1 month. That base density is risk neutral. All the densities here are risk neutral. There's no physical density anywhere. And there's a rebate function, and there's a set of measures. So, okay, well, a typical solution of this problem, wait a minute, I've gone too far the other way. Oh, yeah. So that is, so those are the ingredients of the DSP. And then a typical solution on SPY was buying what looks like a capped strength. Okay, I'm not just selling out of the money puts as I do in a PQ trade. This is the optimal measure change density that comes from the saddle point. And so I implement this every day from January 3, 2017 to December 31, 2024 on SPY, taking on the position the machine is telling me, unwinding legacy positions at 5% every day, and then constructing the cumulative cash flow from the option trade. And so this was the cumulative cash flow using SPY. Then I also did a similar strategy for Apple and a similar strategy for Amazon. Basically, that's the story. There's a new objective function to be used for the financial decision making. The ingredients are a cone of acceptable risks and a rebate function that tells you limit on the losses you're willing to take. And then you solve the dual saddle point problem, and it tells you what to do. And then you can turn that into a strategy. So that's why I'll stop there. Thank you very much.
Is there any question?
Yes. Yeah. Thanks a lot for the presentation. Just a question. The link between this theory and the Gilboa-Smiley max mean expected utility, max mean expected utility, and max mean problem has been around a lot. I'm asking whether your decision maker is maybe too conservative, and whether the rebate function is actually a way of modifying the degree of conservativeness of the decision maker, because you are always keeping a solution at as I understand, at the border of these minimizing with respect to P, which is different between with respect to taking the maximum of the typical mean variance or other kind of solution.
Yeah, I have written a paper on risk attractiveness, where I show that using a concave distortion is a conservative, too conservative, not only conservative, but guaranteed to lose money strategy. Okay. And that the strategies that are actually positive in value use distortions that are convex in some regions. And so you can apply convex distortions that are both convex and concave, and I've started using them. And the interesting thing about those distortions is it's a non-convex, non-concave problem, but you can always, in many cases, rewrite a distortion that is not concave and not convex as a difference of two concave densities, as a two concave distributions. Or you can write it as a difference of two convex, they come together. And so that takes you into the domain of DC programming, that is difference of convex, okay? And so you can go, and so you can say that I'm going to now use not this value function, but a difference of two such value functions, okay? And that will probably trade better because it combines concave and convex. But then developing the algorithms for the difference of saddle points, okay? That's taking you to DDSP, that is difference of discipline saddle point. At the moment, that doesn't exist for fast computation, but maybe we can get there. But yes, so I agree that you may, in that interest, move away from strictly concave to difference of concaves.
Yes, quick one, yeah, because we are.
Why did the LTCM give back 2 billion? Because there is a cost in rebates, right? So this is not included in the model.
That's right. The thing with the rebate and the cost of the rebate is that it is sitting there, okay? You take Morgan Stanley, it's sitting in the trillions, okay? And the trading desks are playing at most in the billions.
But for TCM, it means
They were too thin, okay? They were not a big shot, okay? And so they actually didn't have enough money to make.
Thank you very much again.